All right, let's get started. All right, so attendance, a couple quick announcements. So attendance grades are up to date. A little bit of a funny story about that. I'm using the same method in my structural analysis class, and some of the students thought it was kind of funny because it's just a link that you could go to the link again and put in another name. So I didn't notice on Wednesday that Billie Eilish was in class. Somebody's been trolling the attendance list, and they've been putting like Jason Voorhees or, different names on the list. I said, that's fine, but the day that you forget to put your own name, it's on you. So, hey, you got to find some humor. I have here that homework 3.2 is currently being graded. I think that one's done. I think I need to turn the column on. I think also homework 3.3 is largely finished, and so if that solution's not available, I'll make that available after class. But homework 3.4 is due today, and homework 3.5 is assigned today, so y'all know the drill. Today's lecture is continuing our discussion of moments and their usefulness, and we have a particular type of system that we're going to be looking at today, and that is the definition of a force couple, okay? And I want to just sort of remind you of something that I showed you at the very beginning of this topic when we first started to introduce the concept of a moment, and that was I had a system that looked maybe something like this, and I had a downward load of maybe 20 pounds and an upward load of 20 pounds. And I said, okay, is this system in equilibrium? So, well, from a sum of forces perspective, yes, because I have 20 pounds going down, 20 pounds going up. So if I were to add up those vectors as if they were a resultant vector, I would get a resultant of 0. But obviously the system is not in static equilibrium because this system, while it might not want to translate, it certainly wants to rotate, right? Well, this particular system and these two 20-pound forces acting together comprise what's called a force couple, okay? And this is a perfect topic to talk about today because we're nearing a very, very important concept with moments, and that's the concept of an equivalent system. And so the best way of introducing what an equivalent system is to start discussing about force couples. So let's go back. Let's make sure that we're clear on the formal definition of a moment. And I'm going to ask a question about this formal definition of a moment because I want to make sure that we're all clear on something. So remember, if I have a point out in space, let's say this point, and I have a force out in space like this, then the moment is defined as R cross F, okay? And R cross F being, F is the force in question, and R being a position vector. And the position vector points from the point in question to the line of action of that force, right? And so we're also saying that the magnitude of the moment is the force times the moment arm, okay? Now, I want to just ask a question off to the side because this is going to be kind of important today. If the force goes through the point in question, okay? So if this, see how here's the point in question, and we have the force flying off out into space. If the force is going through the point in question, what is the moment generated by that force about that point? 0. Exactly right. That's exactly right. Because there is no tendency to rotate, right? And that's one way of thinking about it. Another way of thinking about it, what's your position vector? Your position vector starts at the point in question and points to the line of action. Well, if the line of action goes through the point in question, then your R vector is 0. And 0 cross F is 0, right? So that's just something to keep in mind because that's going to kind of be relevant here in a bit. Okay, let's talk about force couples. Okay, force couples are a pair of forces, two forces that have 3 properties. They have the same magnitude, okay? They have parallel lines of action, and they point in opposite directions, okay? So this would be a perfect example of a force couple, okay? That it is a particular definition, a particular type of system of forces that we deal with, okay? So Now, I propose to you that the force couple, okay, if we look at it from a sum of forces perspective, the sum of forces is 0, okay? But that's where moments come into play, because the sum of moments are not 0. This system definitely generates some moment, okay? Now, I propose that the moment generated by a force couple can be defined as R cross F, okay? And now F being one of those forces, doesn't really matter which one, and R being a vector that starts on the line of action of one force and ends on the line of action of another. So the idea is this. So let's say I consider a point of action, and it doesn't really matter which one. Let's say, let me turn my ink, I don't know, blue. Let's say that this is my point in question. I might have my position vector maybe point like this. This could be R. Let's make that a lowercase r. And so I propose that the moment is R cross F. And the reason why that works is because if I'm summing moments about this particular point, okay, there are two forces. We'll call it negative F and positive F for the sake of discussion. That negative F generates no moment about the point in question, right? Because it's going right through the point in question. So that's sort of the point I was mentioning earlier, is that you can, analytically, one of the ways that you can deal with a force couple is to just look at one force instead of two. That's just a fact I want you to keep in the back of your head, because we're going to use that fact later when we look at the three-dimensional system in our example today. But basically, the idea is if I have, let's say I have a force right here and a force right here, so this is F, and they're in equal and opposite directions, and they are separated by some moment arm d, then the moment is force times d, okay? That's basically the idea of a force couple, okay? It's just trying to recognize that while force equilibrium is satisfied, moment equilibrium is not, okay? And I'm going to show you a couple of instances that I want to sort of get you thinking about this concept of an equivalent system, because it's a very valuable exercise in your understanding of statics. I would argue that when we start talking about equivalent systems, which we're actually going to start talking about on Monday, that's when it gets real in here, if you will. That's when we really start talking about statics, okay? With me so far on this definition? Okay. Now, I want to show you a couple of systems here. I've got three systems here, all right? Now, let's take a look at this system over here on the left. Let's start with this system on the left, okay? So let's think about this from a vector perspective, and let's think of this from a force couple perspective. What do we got? We got a box here. The box has a 20-pound load, pointing in equal and opposite directions. Their lines of action are parallel, okay? And they are separated by a moment of 6 inches, or moment arm, sorry, of 6 inches. So if I wanted to determine the magnitude of that moment generated by that force couple, the math is pretty easy. It's just 20 times 6, which is 120, okay? Now, let's make sure we also understand the direction, okay? Remember this whole right-hand rule that we've been utilizing? The right-hand rule also states that if my thumb is pointing in the direction of the axis, then my fingers are curling in the direction of positive moment. So you're about to see some really horrible artwork on my part, but the idea is that if your thumb is pointing this way, oh God, that's horrible. I'm sorry. I just apologize in advance for that. So the idea is if you point your thumb upwards in the y direction, because think about how these 20-pound loads are going to rotate this box. I mean, imagine the box was sitting there on the floor, and you and your friend were sitting right here, and you were pulling 20 pounds, they were pushing 20 pounds. You're rotating the box like this, right, about the y-axis. And if you point your thumb in the direction of the y-axis, think about how your fingers are curling. you are rotating in the direction that your fingers are curling. So I propose that this system could be represented with the following vector. 120J, and I'm saying it's a positive 120J. It's J because it's rotating about the y-axis, and it's positive because it's rotating positively about that axis. If I were to swap these forces and push this way and pull that way, then I would be rotating the box like this, right? And that would be rotating opposite the direction in which my fingers are curling. Does that make sense? Everybody okay with that? Now, if you're okay with that, now I want to look at this system. So now I've got a different set of forces, but they still fit the definition of a couple. I have two forces that are of equal magnitude. They are pointing in opposite directions, but they have parallel lines of action, and they're separated by a moment arm. So the magnitude of that moment is 30 times 4, which is 120, right? Now, it's still also rotating about the y-axis, right? And it is rotating in the direction of the right-hand rule, right? So I propose that this system and this system can both be represented with 120J. In fact, the same thing is true about this system as well. Does that make sense? I propose to you that from a statics perspective, me as the analyst, I would treat these three systems the same way. They're just moments. Does that concept make sense? Does that idea? That's an important concept to see if you can wrap your head around. See, we're steadily approaching a very, very important topic in statics, the idea of an equivalent system of forces. Let me explain what I'm talking about here. So we typically, as engineers, deal with systems that are subjected to quite a lot of forces, okay? For example, we're going to be dealing with systems in here like truss analyses, where we're going to have forces all over the place. We're going to be looking at the method of joints. There's forces all over the place. Many times, it is easier to resolve those systems of forces into a more manageable set, a smaller, more manageable set of forces. It's kind of like what we did in particle statics, right? If I have an I-bar, and that I-bar has, I don't know, 20 different forces all applied at a common point, what was like one of the most fundamental tasks we did at the beginning of this course? You have a point, you have a bunch of vectors going through that point. How do you add those vectors together and replace them with a single equivalent resultant vector, right? I mean, think about the homework problems that we had where we had P and Q all at the same point, and we're trying to figure out P plus Q. The whole idea was trying to replace those two vectors with a single vector that represented the same equivalent action, okay? The idea is now we have to consider moments, okay? I propose to you that in rigid body mechanics, two systems are equivalent if the sum of forces in system 1 equals the sum of forces in system 2, and the sum of moments in system 1 equals the sum of moments in system 2. So what we'll do is we'll say, I've got a system that has 8, 9, 10, whatever loads on it. Let's simplify it to just a force in the x direction, a force in the y direction, and a moment. Or if it was 3D, Fx, Fy, Fz, and Mx, My, Mz. Just take all those forces and make it a whole lot simpler, okay? Because if we can do that, then we can start to ask, okay, what are now the forces and moments required to keep that system in equilibrium? And now we can start rocking and rolling with being engineers and designing bridges, designing gears, designing pacemakers, designing what have you, okay? Does that make sense? That's kind of where we're going with this. This is where it starts to get real in here, okay? Sound good? Let's do a problem, okay? Now, I'll go ahead and tell you, I will admit just some pure laziness. This is one of the problems that's in the textbook. I really like the problem for the purposes of explaining the concept. But one thing I don't like is, you've got 16 pounds, 16 pounds, 40 pounds, 40 pounds, and then you've got P and P. I wish the image just said 20 pounds and 20 pounds, but because I just want to do the particular case. But it's okay for the sake of discussion. Okay, so I have a system that has a bunch of couples applied to it, and hopefully that's something I want you to recognize. So before, if I said here's a system and there's 6 loads on it, you'd go, oh no. Like, do we have to write vectors and R cross F for every one of those? You just don't like us very much, Dr. Mike. I see how it is. No, it's not that. We can take this and make this a lot easier. So what we're going to do is we're going to take this system of 6 forces and we are going to resolve it into a single vector, okay? And we are able to do that because the 6 forces represent 3 different couples, okay? Just look at the 16 pounds, for example. 16 pounds going up, 16 pounds going down. Equal and opposite direction, parallel lines of action separated by a moment arm. So all I need to do is figure out that couple, and if I can write that in IJK notation, boom, I can get rid of those 2 forces, if you will, and just represent it with a single vector. Same thing with the 40 pounds, same thing with this 20 pounds, the p-values. So that's ultimately what I want to do, is represent these 3 couples as vectors and just add them up. And we're going to determine their magnitude and direction. Okay. No, I don't want my ink annotations. Now, one thing I will tell you is if you scroll down, I've been kind of lazy and I've copied the system over and over again because I kind of don't want to scroll over and over again. I want to kind of have a reference for this. But I just want to have this here. Now, I'm going to help you out with something at the beginning. I'm going to write some point coordinates just so that we have them. So notice this problem is in inches and pounds. So all of my point coordinates are going to be in inches. Excuse me. So let's just get that part out of the way first. So point coordinates, we're going to have A, B, C, D, and E, okay? And so this is going to be 0, 0, 20, 0, 10, 0, 30, 0, 0, 15, 0, 10, and 15, 5, 0. Okay, I'll give you a sec to write those out. But we could just take any one of them and just make sure that we're correct on this. Like, for example, point D. Along the x-axis, we're going this way, positive 15 inches. Along the y-axis, we're not changing at all. And along the z-axis, we're going this way, 10 inches. Okay? So again, it's a useful skill to make sure that you are understanding. And I propose that our ultimate goal is to determine the moment in this system. And the way that I'm going to handle this, which, by the way, let me just do this. Let's say this is 20 pounds and say this is 20 pounds. So that's just me crossing out this and this so that we all kind of see the same thing. What I want to do is I want to see if I can write the moment expression, write each of these couples as a moment. So I propose that ultimately what we're trying to do, and I'm just going to use this shorthand, is we're going to say that the moment due to the 16-pound couple plus the moment generated by, we'll say, the 20-pound couple plus the moment generated by the 40-pound couple. That this is our goal. And if we've got this, we're rocking and rolling, because what's the problem asking? The problem is asking to determine the magnitude and the direction of this, okay? And one thing I hope by now is if you have a vector, if I just give you a vector, you should be able to determine its magnitude and direction pretty easily. Its magnitude, using the Pythagorean theorem, and its direction by getting a unit vector and just taking the inverse cosine of each of those terms, right? That's pretty simple, okay? So let's see what we can do here, okay? Now, I've written it in a particular order. What I did is I did 16, 20, and 40. I really wanted to save the 40 for last, because if you look at the system, the 40 is the one that's kind of on that incline. So let's do that one last. We'll do the hardest one last. But let's do the 16-pound system first. All right? Now, before I move on, am I good? Am I going too fast? Does anybody need a minute? You need a minute? Okay. All right. I'll give you a sec. I need to plug my Surface up anyways. Yeah, don't hesitate. We got plenty of time. All right. Everybody good? And don't worry, this schematic here, I've got it repeating like over and over again, so we don't have to keep doing this. Okay, so what we're going to do is we're going to take each couple one at a time. Let's put this over here. And so I'm going to start with the 16-pound force couple. What's up? Did I skip something? Oh, okay. If you got a question, please don't hesitate. So let's start with the 16-pound force couple. Okay, I'm going to show you two ways of generating the same answer. Okay, because I don't want you to feel like you're handcuffed to doing it one way, and at the same time, I want you to have methods to verify your answers. Because some of this stuff is easier to do by observation, but I want you to feel confident in those observations. So I propose method one is by observation. Okay, so let's see if we can do this from an observational perspective. Let's look at the 16-pound force couple, okay? So I'm focusing on this force and this force, okay? Let's see if we can make some observations. These two vectors, or these two forces, which axis about which does this cause rotation? Will this rotate the object about the x-axis? Like what axis is it? The z-axis, right? Does everybody see that? Okay, so that's a note I want to make. I propose that this rotates about the z-axis. So rotates now. Let's use that right-hand rule, okay? So point your thumb in the direction of the z-axis and ask yourself, is this going to cause positive rotation about the z-axis or negative rotation about the z-axis? Negative rotation about the z-axis. That's exactly right. So negative rotation. Okay? Now, the third observation, what is the moment arm between these two forces? 30 inches. That's exactly right. So I propose then that if FD is what? 16 pounds times 30 inches. I think I can do that math in my head. 16 times 3 is 48, so that's 480 inch-pounds, right? I propose then that that vector is simply negative 480 inch-pounds times K. Why K? Because it's about the z-axis. Why negative? Because we indicated or we discovered based on the direction that it is negative rotation. So, boom. There's the moment generated by that vector, or generated by that couple. Yes, sir?
Why would you not treat it as like a triangle? Like if like the distance between B and C would be the hypotenuse.
That's a great question. So the question is, why would you not treat it like a triangle? Okay, the reason why is because I'm using this definition f times d. Okay, now I'm going to give you two answers to this question. Okay, the first answer is if I use the definition of f times d, d is that moment arm, but what is d? D is the shortest distance between those lines of action, right? So the shortest distance, this is a great question. The shortest distance between this line and this line is that perpendicular distance, which in 3D, I'm sorry, I need to be accurate. In 3D is that distance, which is 30 inches. That's a great question, okay? Now, the second answer I'm going to give you is we're going to do this a different way, okay? And the other way that we're going to do it is we're going to use vector notation, and we're going to see that we're going to get the same answer, okay? So I want to test this using basically your approach, okay? Everybody with me so far, though? So method one is to just look at it. Method two is R cross F. Okay. Now, when you're utilizing R cross F, when it comes to the what you choose as R and what you choose as F, you sort of have to pick a point, okay? And so what I'm going to do is this, okay? I'm going to, let me erase these highlights if you don't mind, because I kind of need the space here. What I'm going to do is I'm going to choose this one here as my F, okay? And so if that's the F, then I'm going to say R starts at this line of action and points to this line of action. So hold on, actually, let me draw that to scale. Okay? So when we use the R cross F analogy, the idea is that first off, we have to pick a point, okay? And so since we're dealing with a force couple, I think it's easiest to just pick a point that lies on the line of action of one of those forces. Doesn't really matter which one, okay? So since I'm picking this is my point, we're going to say that this is my force, and we're going to say that R starts at B and points to that line of action, okay? So watch what happens, okay? Let's start off with F, okay? Can anybody tell me what is a vector definition for F? Do we have to do lambdas and all that, or can we look at F and see, like, what direction, what axis is that force pointing? The negative y, right? So I propose that F is simply just negative 16 J. Is that fair? Is that a fair definition? So do that a little better. Okay? And as for R, I propose that R is simply going to be the vector BC, from B to C. Okay? So the way that we're going to do that, if you don't mind, I'm going to scroll a little bit. Let me move this out of the way. So the way that we're going to do BC is we're going to take the coordinates of C, which we already wrote down as 30, 0, 0, and we're going to subtract the coordinates of B, which is 0, 10, 0. And so if we subtract those, we get 30 minus 10, 0. And so therefore, R is going to be 30 inches times I plus negative 10 inches times J. Okay? Now, to scroll up a little bit so that you can see, would you agree that that is a fair definition of R, right? We go along the positive x-axis, go down the y, and we don't change along the z. Is that fair? Okay. So method one was to look at it. Method two is to do R cross F. Let's do R cross F. So let's see what we get. Again, I'm going to drag this thing down. Sorry. So let's do R cross F. So ijk for the r vector, 30, -10, 0. And then for the f vector, 0, -16, 0. Okay? So again, the f vector just has a term on the j direction, right? And then r has ij, no k's. So cofactor expansion, cross out the rows and columns, minus j, cross out the rows and columns, sorry, hold on, plus k, cross out the rows and columns. And let's see what we get. What happens when we cross this out? What do we do? Okay, so for the I terms, 0 minus 0 cancels. What about the j terms? 0 minus 0 cancels. What about the k terms? Okay, this minus that. That's 0, so all we have is 30 times -16. And what's 30 times -16? -480. And by golly gosh gee, that is the exact same thing we got by just looking at it. Make sense? So the point I'm making is I want you to develop those skills of observation, but I also want you to have a tool to verify those observations. And that goes to the question that the gentleman asked in the back is, why aren't you using that diagonal distance, that hypotenuse, if you will? Well, you can, but you got to do R cross F, right? You have to use the formal definition of the moment, okay? Does that make sense? And does that sort of now fully answer that question? Good deal. Like that. All right, any questions? Okay, so if that's the case, now let's be engineers. Okay, let's not be mathematicians, let's be engineers. Okay, so if you remember this problem, we have three vectors, or three couples. We have, let's pull this up here, let's make sure that we're looking at this, okay? So we have a 16-pound couple, a 40-pound couple, but we also have this 20-pound couple. So let's do that, the 20-pound force couple. Now, before we start barreling down the road of doing both of these methods, let's be engineers. Let me ask you a question. Do you propose that it would be easier to do method 1 or method 2 for the 20-pound force couple? Method 1, exactly right. Because with method 1, the rotation is clearly about a particular axis, okay? So let me ask you, about which axis does this generate rotation? The y-axis, exactly right. So let's do some of those observations. This rotates about the y-axis. Now, let's break out the right-hand rule. Let me ask you a question, a second question. Does that generate negative rotation or does that generate positive rotation? Positive rotation. So we have positive rotation about the y-axis, positive rotation. Okay? Now, what is the moment arm between these forces? There you go. Now, does everybody see that? So what we're doing is we're saying, let me use my little extension here. We're talking about the shortest line of action. And so the shortest line of action is this distance right here, right? And so that distance is basically that right there. So it's 30 inches. So therefore, come on, therefore, FD is 20 pounds times 30 inches. 20 times 30 is 600. And so therefore, I propose that M20 is positive 600 inch-pounds times J. Okay, does that make sense? Just look at it. Don't make it harder on yourself, okay? If you want to break out R cross F, you can. I think you're just going to be wasting time, okay? Now, so we've taken care of the 16-pound force vector, force couple. We've taken care of the 20-pound force couple. What about the 40-pound force couple? Which method do you think is best for that? I would use method 2. The rotation, the axis of rotation is a little more complicated because the forces are all, inclined. So I would just trust R cross F. Just let R cross F do the work for us and figure out the components along each axis, okay? Don't try to do that in your head, I don't think I could do it in my head without doing R cross F. So 40-pound force couple. Let's use R cross F. So I'm going to copy this image one more time. Again, so I don't keep having to scroll. So what we're going to do for the 40-pound force couple is, again, we just pick one point to be on the line of action of one of those forces. So what I'm going to do is sort of pick this force this point right here, okay? So we'll say that's the point about which I'm summing moments, okay? And all we need for our position vector is that it points to the line of action of the other force. So we could use BD as our position vector. We could use BE as our position vector. Either of them is correct. You could use either one. Hopefully you found on the homework that you turned in just now, it doesn't matter what the position vector is. If it starts at the point in question, ends on the line of action, you get the same answer regardless. So what I'm going to do is this. I'm going to use BD as my R vector, okay? And I'll use DE as my force vector. And I'm going to get you to help me out a little bit on this. So for BD, I need the coordinates of D, the coordinates of B, okay? So D was 15, 0, 10, and B is 0, 10, 0. I'm actually doing it a different way that I'm doing here on my little calculations here, so I'm going to need your help. So what do we've got? We've got 15, negative 10, 10. Is that a fair statement? So would R be 15I plus negative 10J, let's see, plus 10K? Let's color that like in blue. And we'll say in inches. Is that a fair statement? Okay. For the force vector, unfortunately, we got a little bit more work to do, right? Because what we have to do is we have to take the coordinates of E minus the coordinates of D. So let's do that. So let's see. I got to go back here. So E is 15, 5, 0, and D is 15, 0, 10. So what do we got? 15 minus 15 is 0. 5 minus 0 is 5. Negative 10, right? So what is this? DE is 0I plus 5J plus negative 10K. Is that a fair statement? All right. Now, this isn't enough, right? Because this is just a distance vector. To get a force vector, we have to take this, turn it into a unit vector, and then take that unit vector and multiply it by 40 to get a force vector. So let's do that. So what's the magnitude of DE? It's 0 squared plus 5 squared plus negative 10 squared. I don't think this number comes out all that pretty. So what is this? 11.18. Give me one more decimal place. And that's inches. Do I have a second on that? Okay. So we need lambda DE. So let me scroll down a little bit and get myself some room. So we need to do 0I plus 5 over 11.180 times J plus negative 10 over 11.180 times K. Okay? And I want some precision on this. So let's do, I don't know, like 3 decimal places. So, because if you follow all your decimals, when you multiply out F and then you multiply R cross F, the accuracy is sort of like maintained in the end. So, let's see. So that's 0. Give me like 3 decimal places on that. And then what about this? This is going to be negative. That's right. In fact, I used a completely different vector, and because I looked at the other force, I got the same answer, just my signs were flipped. Like I did mine the other way. Instead of summing moments at B, I summed them at D. So my answer is a little flipped. But so far, so good. So all we have to do now to get our force vector is take lambda and adjust it by the magnitude of that force. So 40 pounds, 0I plus 0.447 J minus 0.894 K. And so F, I think when it's all said and done, you're going to get 0I, and you're probably going to get something like what? 17.889 pounds? And then you're going to get something like, oh, I don't know, 35.777 pounds. Let me just do the units at the end. I forgot a hat on that one. What do you think? So far, so good? Okay. So now that we've got this, we've got R, we've got F, all we've got to do now is cross those to get the moment at 40, or the moment due to that 40 couple. So, cheat a little bit here. So, 15, 0, and then 17.889 -10J, and then 10 negative 35.777K. I believe that that is correct. Now I'm curious. Well, here's what I'm going to do. Given that we're starting to crunch a little bit on time, what I'm going to do is I'm going to tell you what you should get, okay? What you should get is the following. 178.89I plus 536.66J plus 268.33K if you do this by hand. I'm hoping that by now you can actually do the cross product, but I mean, I can tell you, here's an example. When we do the K term or the I term, so we're going to cross out that. So what's this times this minus this times this? Boom, I can tell you that's going to work out. When we do, let's say, the K term, cross that out, we're going to have 15 times this. Just as a spot check, what's 15 times that? Should be that. Does that make sense? Like, hopefully by now I can sort of skip that part. Okay, let me see if I can summarize this problem real quick, because I know it's Friday and y'all want to get on out of here. So what I want to do ultimately in this problem is sum these vectors up. Okay, so summing up moment vectors. So here's what we've got, okay? We've got M16, M20, and M40. Now M40 was the complicated one. What did we get for M20? What was that? 600J. So what I'm going to do is I'm just going to sort of write it like this. Put it like over the J term. And then for the 16, how we got minus 480K, I'm going to put it like this. And that way when I add them up, I can just add them up in columns. So I propose that the total moment for this entire system is 178.89I, right? For the J terms, take this plus this. When you add them up, you'll get something like 1136 times J. And then for the K terms, what we got to do is we got to do this plus that, but because it's negative, we're going to have a negative term here. Negative, 211.67. So we took all those 6 forces and replaced them with a single vector. And then I'll just do this real quick. If I wanted to determine the magnitude of that moment, just how much moment it is, just do the Pythagorean theorem, and you get 1169.95. And then if you want to determine direction, take the moment vector, divide it by its own magnitude, and when you do that, you'll get 0.153I plus 0.972J. I'm going to leave this up here when we call it, minus 0.181K. And so all you have to do is take the inverse cosine of these terms, and you get 81.2 degrees 13.7 degrees, and 100.4. Sorry for keeping you another 1 minute, but I'll leave this up here. I'm going to stop the recording. I'll leave this up here. Y'all have a wonderful weekend.